This is Pre-Calculus, Functions and Graphs. I'm Mr. Stark. We're wrapping up Topic 4, Building Functions from Functions. And this is Lesson 4b, Relations and Implicitly Defined Functions, or more appropriate, curves. You can follow along using this document where we'll define relations and contrast explicit versus implicitly defined functions. There's also a bonus example about completing the square. Let's get started. Let's start with relations. A relation is a set of ordered pairs, x, y. Some relations are functions, but all functions are relations. We can sketch a simple Venn diagram to demonstrate that idea. We have functions on the inside and relations on the outside. All functions are relations, but there are some relations that are not functions. Here's a specific relation, x squared plus y squared equals 4. This equation represents a circle centered at the origin with radius 2. It's not a function because it fails the vertical line test. There are multiple y values that correspond to each x value. Algebraically, the relationship is special because all of the ordered pairs, x, y, are solutions to that equation. Also, geometrically this relationship is special because the points form a circle. So let's say you wanted to see this relation graphically. I found that there are a few ways to do that without too much difficulty. One way is to solve the equation for y so you can plug in x values and then plot the points by hand. Another way is if the curve is a circle, an ellipse, a parabola, or a hyperbola, you can use the Conics app on a TI-84. You can look in a textbook to see what the formulas are for those curves. Oh, and if you don't have that app, you could download it from the Texas Instruments website. Now let's talk about implicitly defined functions, or as I call them in the title, implicitly defined curves. First, let's make sure we understand what implicit and explicit mean. Explicit is an adjective that means stated clearly. So when we state a function clearly, we do that by saying y equals and then what the formula is. On the other hand, implicit is an adjective that means implied and not clearly expressed. So when we express an implicitly defined function, we don't have y equals. We have a combination of x values and y values and numbers in the equation. That's why the circle defined by x squared plus y squared equals 4 is implicitly defined. It's not solved for y. So let's try to make it explicit. What we could do is subtract x squared on both sides so that we get y squared equals 4 minus x squared. Then we take the square root of both sides to get y equals positive or negative square root of 4 minus x squared. Some students are tempted to take the square root of 4 and x squared because they're both perfect squares, but that's not allowed. If 4 and x squared were being multiplied, we can totally do that. But because it's a subtraction, or if it was an addition, then we can't do that. So we have two explicitly defined equations. Y equals positive, square root of 4 minus x squared, and y equals negative, square root of 4 minus x squared. The positive equation is the top half of the circle, and the negative equation is the bottom half of the circle. Separately, both of those equations are functions, but together in one equation, x squared plus y squared equals 4, it's a relation. Like I mentioned earlier, we could use both of those equations to plug in x values and then plot that graph by hand, or we can plug those equations into y1 and y2 on a TI-84 calculator and see what the graph looks like. Those are the main ideas for implicitly defined functions. I have one more bonus example that includes completing the square. You can check it out if you like. Here's a more advanced example. Describe the graph of 9x squared plus 4y squared minus 24y equals 0. Just by looking at that equation, it's hard to really know what that'll look like on a graph. So let's try to solve for y. First, let's factor a 4 out of the terms that include y variables. So we have 9x squared plus 4 parentheses, y squared minus 6y, close parentheses, equals 0. What I see now is a potential to use completing the square with y squared minus 6y. So I rewrite the equation to include a box where we would enter a number that would complete this perfect square. And if I add a number to the left side of the equation, I have to balance that equation on the right as well. Here's the shortcut. We take that negative 6, divide it by 2, and square that number to get 9. 9 completes the perfect square. Then, because that 9 would eventually multiply by the 4 to get 36, that's what I add to the right side of the equation. The next step is to factor that perfect square. So we get 9x squared plus 4 quantity y minus 3 squared equals 36. Now we're mostly home free. We subtract 9x squared from both sides. 4 times y minus 3 squared equals 36 minus 9x squared. Then I divide by 4, take the square root of both sides, so I get a positive and a negative. Then I add that 3, and now I have two equations. I have a positive square root of a bunch of stuff plus 3, and a negative square root of a bunch of stuff plus 3. Remember, I can't take the square root of 36 and write 6 and 9x squared and write 3x, but I can take the square root of 4 and write that as a 2 outside of the square root. I don't really see much purpose in doing that, especially if we'll plug that into the calculator. And when I enter both of these equations into the calculator, I can see that it gives me the graph of an ellipse. Looking back at the original equation, the reason why it's an ellipse is because the coefficient of x squared is different than the coefficient of y squared. If they were the same, then it would be a circle. Well, if there's anything I learned from this lesson, it's that not all relations or relationships are functional. But that doesn't mean we can't learn something from them. I hope you learned something, and I look forward to teaching you again soon. Thanks.